Hello and welcome. Today we are here to talk about the muscle fatigue sensor that we have created. I am Sam Holden. Joining me are Amit and Masa, Anamika, and Kuro. Lifting weights and working out are everyday activities for many healthy people. Undergoing these activities can cause muscles to fatigue and become weak. Muscle fatigue is caused by a lack of oxygen or blood flow to the muscles, but there is no widely used quantifiable muscle fatigue measurement. Excessive exhaustion of muscles can decrease their efficiency and cause muscular strain. Due to these reasons, and because people want to know as much about their health as they possibly can, it becomes necessary to design a way to detect and quantify muscle fatigue. This project aimed at designing a muscle fatigue sensor using a connected mobile application which can keep track of how fatigued a user's muscles become. A few months ago, we gave a presentation on this subject to our medical devices class, and we are at a significant point in the device development. We had designed and built a basic EMG sensor for reading muscle activity. Our app was functional in that it was as far as we could take it before we had any actual recorded data to compare it to. We had measured some small amounts of fatigue data and begun to see the waveform shapes that would bring us to being able to distinguish between fatigued and non-fatigued muscles, and we could display those waveforms to the computer. Well, today I'd like to tell you we have continued to build upon that success and announce that we have created a working EMG-based muscle fatigue indicator. Our hardware has been moved to a prototyping board and correctly filters the type of signal we want. Our software reads that EMG and determines which signals indicate fatigue and which do not, as well as telling you your peak signal value as a fatigue level to compare to your friends. In this slide, you see the block diagram of how our device works from input to user interface. We are still working on making the fabric electrodes function consistently, so we are using disposable ECG electrodes to gather our data. The raw data is then put through the amplification and filtration circuit described by Masa in the next slide. Once filtered, the signal is read by the analog to digital converter on the Arduino microprocessor, and the results are sent through a Bluetooth communication unit to a mobile application on the user's phone. The phone then processes the signal and displays results along with any related messages to the user.
EMG is a very low voltage noisy signal. Therefore, we needed to design a good amplification and filtering circuit. For amplification, we used an instrumentation amplifier because it has relatively a good CMRR, which helps with reducing noise at the first stage. Considering the EMG voltage range and the op-amp's voltage ranges, we set the gain of our amplifier at 100. For the filtering circuit, based on our researches, we found out that the EMG frequency is almost between 10 to 500 Hz. In practice, by using the Salenki filter topology, we were able to design a bandpass filter with its high and low frequencies set at almost 7 and 480 Hz.
Our initial design began like many on a breadboard. We used an LM324 operational amplifier circuit to read the signal and send the data to our Arduino analog to digital converter to read. The Arduino then sends that data on to a Bluetooth BLE module to be sent to a mobile application on the user's phone. The entire system currently runs on a 7.2 volt battery pack, but we are working on ways to reduce the power cost so we can make the device more compact without sacrificing battery life. Once we had achieved a fully operational breadboard prototype, we moved on to soldering the circuit to a small prototyping board to reduce space and make the device more presentable. In the future, we are planning to implement our device into a shirt design as shown on the next slide, or a small workout armband, but we are still working on the specific details of how to make those function. In this slide, we have the current and future iterations of the device. In the picture on the left, we are keeping the circuit in the box on the waist and using disposable ECG electrodes on the right bicep under the shirt. Our current goals revolve around using fabric electrodes sewn into a tight-fitting shirt or armband as shown in the picture on the right, with a detachable circuit to remove the need for excess gear and allow the clothing to remain washable. Now it is time to talk about the results we were seeing in our experiment. For this experiment, we used 2 ECG electrodes placed 1 inch apart on the dominant bicep of 5 different users. The users then performed bicep curls to simulate a standard exercise in a gym. A 10-pound weight was used for all users, and they performed the exercise to exhaustion. After around 100 times amplification and filtration, the resting value of the muscle was between 0 to 100 millivolts. These starting values that we were seeing from compressed muscles were around 75 to 200 millivolts depending on the user, and we initially expected this number to go down as the nerve became more fatigued, like one would see in results from a muscle fatigue sensor based on a steady grip. Instead, to our surprise, when the muscles fatigued, they increased to around 300% of the initial starting value. We postulated that this was due to the nerves having time between repetitions to rest and recharge, while the muscle fibers did not. The distinction would cause the nerves to need to send more stimulating signal in order to achieve the same results from a set of tiring muscle fibers. We also observed a noticeable difference in results between users, but these results did not seem random. The stronger users seemed to be able to produce higher voltages, especially when they had them lift heavier 25-pound weights to compare.
The algorithm. This slide describes the block diagram of our algorithm. We use a very simple algorithm that uses ADC functionality of Arduino to get the reading from our filter circuit and analyze it to detect muscle status. As we found different voltage reading values for different people, we take the average of peak voltages in the readings in order to set a base value of normal muscle health for the users. After this, we read the EMG signal regularly to check if it crosses the 200% mark of the base average value that we had initially calculated. When we get signals that cross this level, we send an alert signal via Bluetooth to the cell phone, which alerts the user. The app. As everyone uses cell phone, we decided to make an app which could monitor the status of muscles. The app allows you to connect to the Arduino on board our device and exchange information. The Arduino processes the signal it gets from the amplifier and filter circuit, and at regular interval updates the muscle status via Bluetooth to the mobile app. The mobile alerts the user whenever it gets messages that indicate muscle fatigue.
Here is a small demonstration of us using our muscle fatigue sensor.
What you see here are gel electrodes connected to a subject's arm along the bicep, reading the surface EMG signal. The signal goes to our PCB for processing, where it is amplified and filtered to carefully reduce noise from motion and other non-muscular sources. For this reading, the subject is performing bicep curls with an 8-pound weight, allowing him to lift it for long enough to firmly see how the signal changes as the muscle fatigues. Currently, we are looking at the peak values from each lift. The algorithm watches the first 5 lifts of the weight to calibrate a starting value for each individual user. These peaks gradually increase as the muscle becomes fatigued because the neurons have to fire more often to stimulate the worn-out muscle. When these peak values reach a certain threshold above the starting value, the device sends a Bluetooth signal to your phone letting you know that your muscle is fatigued.
Our future plans for this device involve allowing the app to store peak values and compare them against your friends to prove who is working out harder. We wish to fully implement the circuit into a shirt design with reusable fabric or other electrodes. Our plan then is to add in compression socks and shorts and find ways to properly measure those results in order to compare the data to cardio data in long-distance runners and soccer players to see what is slowing you down, since we've had a lot of interest in that from the sports science people we have interviewed. We want to reduce motion artifact and replace the gel electrodes with dry electrodes and turn this system truly washable and wearable. If you have any questions, please tweet them at us using hashtag VCACS2016_SAH. Thank you for watching.